This video is on solid revolution using the shell method. So here we have the function f of y, which is this graph right here, and then the function g of y, which is this graph. And then we have the yellow region right here, and we're going to revolve it about the line y equal to 3. And this is the solid revolution, and we want the volume of this solid revolution. So here's the yellow region again. So the axis of revolution here is the line y equal to 3. So the first thing that we need to do is find the point of intersection right here, where the graph intersects with the y-axis. And then we also need this point of intersection right here. So at this point, the x is 0, so we just need to find the y. Here's the graph of f of y, and we want this point right here, so we want the y-intercept. So to get the y-intercept, we just set the x to 0. So we have the third root of 2 minus 0.4y to the third plus 2 equal to 0. And then subtract 2 from both sides, and then raising both sides to the third power. Then we get 2 minus 0.4y to the third equal to negative 8. And then dividing both sides by negative 0.4. Then we get y to the third is equal to 25. So we get y is the third root of the cube root of 25, which is 2.92401. And so this point right here, the x is 0, the y is 2.9240101. And then now we need to find this point. So to find the point of intersection, first what I'm going to do is I'm going to go ahead and solve both of these equations for y in terms of x. So this first equation right here. So first subtract 2 from both sides, and then raising each side of the equation to the third power, and then we get this line right here. And then move the 2 here to the left side, and then we end up with negative 0.4y to the third, x equal to x minus 2 to the third minus 2. And then dividing or multiplying both sides by negative 2.5, and this is what we'll get. And then taking the third root of both sides, and we end up with y is equal to this. This equation right here, y for this equation, y is equal to this, and then the x equal to 4y, y is equal to 0.25x. And then set the two equations equal to each other, and then solving for x, that will give us the x coordinate of this point of intersection. So let's call h of x this function right here. And then to find this point of intersection, what we can do is use what's called Newton's method. And to use Newton's method, we're going to need the derivative of h of x. And so here we have 1/3. Notice that the third root here is the same as exponent of 1/3. So we get 1/3 times all of this right here. And then 1/3 minus 1 is negative 2/3. And then the derivative of this part is negative 2.5. And then times 3. And then times x minus 2. And then 3 minus 1 is 2 here. And then the derivative 2 here is just 0. And then derivative of negative 0.25x is just negative 0.25. So this will be h of x, and this is the derivative of h of x. And then now we can use Newton's method to find the x, the solution for this equation right here. To use Newton's method, let's go ahead and look at the graph of h of x and see where it crosses the x-axis at. And so here's the graph of h of x, and it looks like it crosses the x-axis at about 3.1. And therefore, I'm going to use the initial guess of 3.2. And then using this Newton's method's formula to calculate x sub 2, then we get 3.216179. And then the next iteration, x sub 3, then we get 3.214734. And then after 8 iterations, we get 3.214717. And so at the point of intersection, so for this point of intersection right here, x is 3.214717. And record that x right here, x is equal to 4y, and so y is equal to 0.25x. And so in the place of x, if we use 3.214717, then the corresponding y would be 0.803679. And this is the point of intersection for this point right here. And now I want to show a little bit how I got to this value right here using Newton's method. Here's an illustration of Newton's method. So this is h of x, and this is the derivative of h of x, and then the initial guess of 3.12. So after the first iteration here, we got the solution to be approximately 3.216179, and then continue on to the other iterations. And so here's after 8 iterations, and so we got the x-intercept right here to be about 3.214717. And so that's Newton's method. And so here's the points of intersections once again. And now let's revolve it about the line y equal to 3. And so this is what the solid of revolution would look like. And then we're using the shell method, and so I'm going to fill the solid of revolution with cylindrical shells that would look like this. And so here I divided the solid of revolution into 8 shells. And here are the calculations for the volumes of the 8 shells. So altogether, the volumes of the 8 shells, they're about 53.6177. And then we want the more exact answer. Then we have instead of 8 shells, we have to divide the solid of revolution into an infinite number of shells. And so here's what the ith shell looks like. This is one of the shells. So the distance from the axis of revolution to right here, that's the inner radius. And then the distance from the axis of revolution to here, that's the outer radius. And then right in the middle right here, at this midpoint right here, so the distance from here to the axis of revolution, we call that the average radius. And so this midpoint right here, let's call it y sub I star. And therefore the average radius for this ith shell would be 3 minus y sub I star. And to get the height for this ith shell right here, and so we need to notice something right here. For this particular solid of revolution, from here to here, from the x-axis to 0.836, the shell is bounded by the y-axis in this graph. And then from y equal to 0.836 up to y equal to 2.94, the shells are bounded by the y-axis in this graph. And so to calculate the volume of the solid of revolution, we have to break it up into two parts. So we have to integrate from 0 up to 0.8367925 using this graph. And then from 0.8367925 up to 2.9401771 using this graph. And so for shells from 0 to 0.0836, the height of the shell will be g of y sub I star. And then from 0.8367925 up to 2.9401773, the height of the shell would be f of y sub I star. And the volume for the part that's from y equal to 0 up to y equal to 0.836 is going to be 2 pi, and then the integral from 0 to 0.8036, and then the radius is 3 minus y. But then once again, from here to here, the height is going to be bounded by the graph g of y, and g of y is 4y. And then evaluating this integral, we get 20.00109. And then for the part that's from y equal to 0.8036 up to y equal to 2.940, the height will be the function f of y. And so we get the radius, and then the height, and then the thickness. And then evaluating this integral here numerically, using numerical integration, then we get 34.3375. And then adding the two volumes here together, we get 54.33. So the volume of the solid of revolution that we want is 54.33. And now we compare this answer here to the answer when I divided the solid of revolution into A shells, then into A shells, then the answer was 53.61, and then we can see that it's very, very close. And that's the end of the video.